we're going to be thinking about the reflection property and parabolas. Now, when some object, whatever it happens to be, it might be a photon, it might be a marble, hits some surface, it's going to bounce. And it's going to bounce in terms of the so-called equal angles principle. And the equal angles principle itself is based on the path of that object, of that photon, of that marble, with the tangent line to the surface at the point of contact. So right now we have a parabola. We might imagine it is a satellite dish and it's taking in photons. Right now we have y is equal to x squared, but we can think about a more generic parabola like y is equal to ax squared. The center of axis goes right through the vertex of the parabola, and this parabola's vertex is at the origin 0, 0. So let's say some photons are coming in, and the key here is that, and I'm just going to extend this line for geometrical purposes so we can analyze this, is that this line here is parallel to this line here. So they're parallel. Now with the reflection property, the photon comes in, strikes the surface right here, and the cool thing is that it will bounce to the focus of that parabola. So the focus is right here. And so now let's just connect these two. So the photon bounces to that focus. So get this approximately right. Okay. Now let's right now think about this parabola. Now in general, if we think about the definition of a parabola, we can derive its equation. We've done that in a previous video. So we have a parabola such as x minus h quantity squared is equal to 4p times the quantity y minus k, where the vertex is located at h comma k. Moreover, the absolute value of p, for example, is the distance from the focus to the vertex. So presently we have y is equal to ax squared. But let's put it in this form here. So we'll get x squared is equal to 1 over a y. So from that we can read off, so to speak, the vertex, which is at the origin 0, 0. But also note that 4p equals 1 over a. If we solve for p, we get 1 over 4a. So this allows us to determine the focus and also the directrix. So if we think about the focus, we have 0, 1 over 4a. We can then, for example, think about this point over here. So what would that be? And what would this point up here be? We just have this parabola, and we're going to say that just some, so to speak, arbitrary point. And we'll say that is at x naught, comma, a x naught squared. And then from there, we can determine this point over here. So that would be at x naught, comma, let's think about what we found out down here, 1 over 4a. So it would be negative 1 over 4a. And finally, we should think about the tangent line. So let's get that tangent line in. And this is going to be pretty rough. I'm going to try my best to get halfway decent. So we have this point up here. I drew that point so large that makes it more difficult actually to get. So the tangent line just goes through that point on the parabola, and that is it. So it shouldn't intersect any other point. We don't want a secant line, we want a tangent line. So this is going to be very, very rough for our purposes. I'm sorry if it's not as good as it should be, but the problem is also is that this line might be too thick. Just see how this looks. Ooh, Well, for our purposes, I guess that will work. It's not ideal, but that's the tangent line. So what we're going to try to do, so to speak, is to verify this reflection property given what we have. So that means we're going to want to think about some of these angles. So on the one hand, you have this angle here, so from this green line to this blue line, and we'll call that theta 1. Then you have this angle here, from that green to blue line, we'll call that theta 2. And this blue line to this green line here, we'll call that theta 3. And we want to show that theta 1 happens to equal theta 2. Now there's several things we can note. If you look really, really close and squint your eyes, in fact, this angle here and this angle here are opposites. But if that's the case, then we know that theta 1 equals theta 3. Then the issue is, could we show that theta 2 is equal to theta 3? And if we can show that, it would therefore follow that theta 1 is equal to theta 2. Now there's a triangle here. So let's consider this triangle. So if we go from 0, 1 over 4a to x naught a x naught squared, and then from that to x naught, negative 1 over 4a, and then if we connect those two, we get this. Now this is isosceles because this point here, this arbitrary point on the parabola, is equidistant from the focus and the directrix. So this line segment, this line segment are definitely equal. And now, if we think about that tangent line, so this is the tangent line, remember, we can think about its slope. There are different ways to calculate it. The most convenient way is through calculus. And technically, I'm not supposed to be covering calculus in this video, but because it's convenient, I will. But there's other ways to do this. So remember, we have y is equal to ax squared. And we're thinking about the point x naught, a x naught squared. So the slope of tangent line is 2ax naught. And then if you figured out the slope from this point, 0, 1 over 4a, to this point, x naught, negative 1 over 4a, you would determine that the slope there is negative 1 over 2ax naught. Now notice this. Notice that 2ax naught times negative 1 over 2ax naught is equal to negative 1. So that implies that we have perpendicular lines. So here we have a right angle. Moreover, that tangent line divides that isosceles triangle with two congruent halves. So that implies that this right here and this right here are equal. But if that's the case, it must be that theta 2 equals theta 3. But if theta 2 equals theta 3, because we know that theta 3 equals theta 1, it therefore follows that theta 1 equals theta 2. So this actually proves the so-called reflection property. It's a very interesting property because in the real world it shows up. We can think about satellite dishes. We can think about the parabolic mirror in a telescope gathering and focusing in that light. We can think about the headlights to a car. Those are parabolically shaped such that the light doesn't spread out all over, so to speak, to blind everyone while we drive. So this is the reflection property